1, 2, 3. Let me just quickly make sure that stream is actually online running. Alright. Check that I'm actually unmuted this time, instead of accidentally having my stream be muted for like 30 minutes. That was embarrassing last time. Okay. Then with that, again, I won't delay. I'll just get straight into it. Chapter 8, Algebraic Coding Theory. Coding theory is an application of algebra that has become increasingly important over the last several decades. When we transmit data, we are concerned about sending a message over a channel that could be affected by noise. We wish to be able to encode and decode the information in a manner that will allow the detection, and possibly the correction, of errors caused by the noise. This situation arises in many areas of communications, including radio, telephone, television, computer communications, and digital media technology. Probability, combinatorics, group theory, linear algebra, and polynomial rings over finite fields all play important roles in coding theory. 8.1 Error detecting and correction codes. Let us examine a simple model of communication system for naming and receiving coded messages. Figure 8.1, which is actually this. So we're gonna write this here. So we have encoder. Encoder to the transmitter to the receiver to the decoder to the receiver to the decoder. So we take a message M, put it in, and then through this we should get a message M back on the other side. And mainly we'll be worrying about the noise from the transmitter to the receiver. Because imagine the transmitter is like you broadcasting a signal, and the receiver is like a satellite dish that takes in a signal. And you can imagine going through the airwaves, air is quite chaotic. There can be a lot of noise in that. So how do we make a system that's robust, in effect, to that? Okay, figure 8.1, encoding and decoding messages. Uncoded messages may be composed of letters or characters, but typically they consist of binary M tuples. These messages are encoded into code words, consisting of binary N tuples, by a device called an encoder. The message is then transmitted and then decoded. We will consider the occurrence of errors during transmission. An error occurs if there is a change in one or more bits in the code word. A decoding scheme is a method that either converts an arbitrarily received N tuple into a meaningful decoded message, or gives an error message for that N tuple. If the received message is a code word, one of the special N tuples allowed to be transmitted, then the decoded message must be the unique message that was encoded into the code word. For received non-code words, the decoding scheme will give an error indication, or, if we are more clever, we'll actually try to correct the error and reconstruct the original message. Our goal is to transmit error-free messages as cheaply and quickly as possible. Example 8.2. One possible coding scheme would be to send a message several times and to compare the received copies with one another. Suppose that the message to be encoded is a binary N tuple, x1, x2, all the way up to xn, which means that x1 is equal to possibly 1 or 0 or 1, x2 is equal to 0, 1, all the way up to xn is equal to 0, 1. The message is encoded into a binary 3n tuple by simply repeating the message 3 times. So x1, x2 all the way to xn goes to x1, x2 up to xn, x1, x2 up to xn, and x1, x2 up to xn. To decode the message, we choose as the ith digit the one that appears in the ith place at the least of the two of the three transmissions. Yeah. For example, if the original message is 0110, then the transmitted message will be 0110, 0110, 0110. If there is a transmission error in the 5th digit, then the received code word would be 0110, 1110. Notice that this 5th digit over here has been swapped from a 0 to a 1. I can't highlight it, but there. Which will be correctly decoded as 0110. Let's also check the footnote. We will adopt the convention that bits are numbered left to right in binary N tuples. Okay. This triple repetition method will automatically detect and correct all single errors, but it is slow and inefficient. To send a message consisting of n bits, 2n extra bits are required, and we can only detect and correct single errors. We will see that it is possible to find an encoding scheme that will encode a message of n bits into m bits with m much smaller than 3n. Example 8.3, even parity. A commonly used coding scheme is much more efficient than the simple repetition theme. The ASCII, or American Standard Code for Information Interchange coding system, uses binary 8 tuples, yielding 2 to the 8 equals 256 possible 8 tuples. However, 7 extra bits are needed since there are only 2 to the 7 equals 128 ASCII characters. What can or should be done with the extra bit? Using the full 8 bits, we can detect single transmission errors. For example, the ASCII code for A, B, and C are A equals 65 sub 10 equals 01000012, which what this is saying is that this is saying 65 base 10, which is equal to this expression base 2. And notice that the leftmost bit is always set to 0. That is, the 128 ASCII characters have codes 000 on and on up to 011111, at least in base 2. The bit that can be used for error checking on the other 7 bits, or the extra bit can be used for error checking on the other 7 bits. It is set to either 0 or 1, so that the total number of 1 bits in the representation of a character is even. Using parity, the codes for A, B, and C now become A equals 010001, B equals 01000010, and C equals 11000011. So, why does this C have a 1? Let's think about this. Well, for A, we have 2 1s, so the entire parity of this number, which is the sum of the parity of every single individual bit, gives us 0. Again, we also have 2 1s. We have an even number of 1s. However, assume that this was set to 0 for a second. Then we would have an odd number of 1s in this, so we would have a non-zero parity. So in order to fix that, we append an extra 1. We change the 0 at the beginning to a 1, so that's always an even number. Suppose an A is sent and a transmission error in the 6th bit is caused by noise over the communication channel, so that 01000101 is received. We know an error has occurred, since the received word has an odd number of 1s, and we can now request that the code word be transmitted again. When used for error checking, the leftmost bit is called a parity check bit. By far, the most common error detecting codes used in computers are based on the addition of a parity bit. Typically, a computer stores information in m tuples called words. Common word lengths are 8, 16, and 32 bits. 1 bit in the word is set aside, and the parity check bit is set aside as the parity check bit and is not used to store information. This bit is set to either 0 or 1, depending on the number of 1s in the word. Adding a parity check bit allows the detection of all single errors because changing a single bit either increases or decreases the number of 1s by 1. And in either case, the parity is changed from even to odd, so the new word is not a code word. We could also construct an error detection scheme based on odd parity. That is, we could have the parity check bit set so that the code word always has an odd number of 1s. The even parity system is easy to implement, but has 2 drawbacks. First, multiple errors are not detectable. Suppose an A is sent and the first and, notice here it's going to be important, first and 7th bits are changed from 0 to 1. The received word is a code word, yes, but will be decoded into a C instead of an A. Second, we do not have the ability to correct errors. If the 8 tuple 1001, 1000 is received, we know that an error has occurred, but we have no idea which bit has been changed. We will now investigate a coding scheme that will not only allow us to detect transmission errors, but will actually correct the errors. Example 8.4. Suppose that our original message is either a 0 or a 1, and that 0 encodes to 000, and 1 encodes to 111. If only a single error occurs during transmission, we can detect and correct the error. For example, if a 101 is received, then the second bit must have been changed from a 1 to a 0. The originally transmitted code word must have been 111. This method will detect and correct all single errors. And table 8.5 is an example of the repetition code. So the code word we try to submit is 000 or 111. And we show we present all possible words that might be received for the transmitted code words. The table 8.5 shows the number bit by which they receive 3 tuples of what differs from the original code word. Something important here to note is that in all cases where we have 2 or more errors, with this above scheme, it actually goes back to the different code word. This is in part fixable. We can optimize this, but it's always important to remember with this that with enough errors, you can turn a valid message into another valid message. So we more so care about maximizing the number of errors that can be taken before we have a scheme that sets us back to our correct values. Maximum likelihood decoding. 4. This section requires a knowledge of probability, but can be skipped without loss of continuity. We are going to just read through this, hope for the best. Oh gosh, wait, while I'm doing this, let me make sure my stream is actually working. Yes, it is working. Okay, that was scary for a second. I thought my whole stream just went blank. Alright, maximum likelihood decoding. The coding scheme presented in example 8.4 is not a complete solution to the problem because it does not account for the possibility of multiple errors. For example, either a 000 or a 111 could be sent and a 001 received. We have no means of deciding from the received word whether there was a single error in the third bit or two errors, one in the first bit and one in the second. No matter what coding scheme is used, an incorrect message could be received. We could transmit a 000, have errors in all three bits, and receive the code word 111. It is important to make explicit assumptions about the likelihood and the distribution of transmission errors so that, in a particular application, it will be well known whether a given error detection scheme is appropriate. We will assume that transmission errors are rare, and that when they do occur, they occur independently in each bit. That is, if P is the probability of an error in one bit, and Q is the probability of an error in a different bit, then the probability of errors occurring in both of these bits at the same time is P times Q. We will also assume that a received n-tuple is decoded into a code word that is closest to it. That is, we assume that the user uses maximum likelihood decoding. For those of you who haven't seen this formulation, this is the same that saying that the probability of error in one bit and the probability of error in a different bit is linearly, not linearly, but not independent, no, are independent events. Which means that the probability that one event is true, given the other event is true, is the same as if the event, we didn't have any supposition to begin with, functionally. That these events don't have any correlation with each other, causally. Alright. A binary symmetric channel is a model that consists of a transmitter capable of sending a binary signal, either a 0 or a 1, together with a receiver. Let P be the probability that the signal is correctly received. Then Q equals 1 minus P is the probability of an incorrect reception. If a 1 is sent, then the probability that a 1 is received is P, and the probability that a 0 received is Q. Example in figure 8, because if a 1 is received, we have a P chance that it goes to 1, and a Q chance that it goes to 0. The probability that no errors occur during transmission of a binary code word of length n is P to the n. For example, if P equals 0.999, and a message consisting of 10,000 bits is sent, then the probability of a perfect transmission is 0.999 to the 10,000, which is, I'm not even going to try to find out what that is. It's a very small number, but it's all you really need to know. And if you don't know why, this is because the probability that in each position there's an error is independent. So the probability that we also have as well a correct transmission is also independent. So to say that this thing with probability 0.999 happens, or an event with probability P happens 10,000 times, means that we roll that P% chance 10,000 times, which is, because of independence, 0.999 times itself 10,000 times, which is why this number ends up being so small. Theorem 8.7. If a binary n-tuple x1 up to xn is transmitted across a binary symmetric channel with probability P that no error will occur in each coordinate, then the probability that there is an error in exactly k coordinates is n choose k times q to the k times p to the n minus k, which n minus k is basically counting up the number of times that you can have q errors or k errors with p successful attempts. And for each of those, we have a probability q to the k, p to the n minus k, again by linear, or not linear, just regular probabilistic independence. Proof. Fix k different coordinates. We first compute the probability that an error has occurred in the fixed set of coordinates. The probability of an error occurring in a particular one of these k coordinates is q. The probability that there is an error will not occur in any of the remaining n minus k coordinates is p. The probability of each of these n independent events is q to the k times p to the n minus k. And the number of possible error patterns with exactly k errors occurring is equal to n choose k equals n factorial over k factorial n minus k factorial. The number of combinations of n things taken k at a time. Each of these error patterns has a probability q to the k, p to the n minus k of occurring. Hence, the probability of all of these error patterns is n choose k, q to the k, p to the n minus k. Example 8.8. Suppose that p is equal to 0.995. So we have that. Let me think how to phrase this. So suppose that there's a 99.5% chance that a message or a bit is sent correctly, and a 500-bit message is sent. The probability that the message sent was error-free is p to the n equals 0.995 to the 500 is approximately 0.082 or 8.2%. The probability of exactly one error occurring is n choose 1 q p to the n minus 1 equals n 0.005. 0.995 to the n minus 1 is approximately 0.204 or 20.4%. And the probability similarly of two errors is 25.7%. The probability of more than two errors is approximately 1 minus 0.082 minus 0.204 minus 0.257. So 1 minus the possibility of everything that isn't more than two errors is equal to 0.457. Block codes. If we are to develop efficient error detecting and error correcting codes, we will need more sophisticated mathematical tools. Group theory will allow faster methods of encoding and decoding messages. A code is an NM block code if the information that is to be coded can be divided into blocks of m binary digits, each of which can be encoded into n binary digits. More specifically, an NM block code. I will actually write this down because this seems like it's going to be a kind of complicated definition. So, NM block code. Block code. Let me write that. It's supposed to say block with the L removed from the O. That was horribly written. Okay. Consists of an encoding function, which takes some z mod 2 of m. So it encodes a block. It encodes a block, or it encodes z mod 2, the m tuple, an m tuple of that, which we call each m tuple a block. And it brings it to z mod n of 2. And a decoding function, which is the reverse. We take some z2 to the n and move it to z2 to the m. Encoding. Decoding. A code word is any element in the image of E. We also require that E be 1-to-1, so that two information blocks will not be encoded into the same code word. So I'm just going to quick injective. I'll also write image of E equal code words. Alright. A code word is any element in the image of E. We also require that E be 1-to-1 so that two information blocks will not be encoded into the same code word. If our block is to be error correcting, then D must be on 2. So I will also put that as something. So error. Oh yeah, okay. Error correcting implies that D is surjective. And the intuition for this is that if there is a code word in ZM of 2, such that, okay, how do I best say that? Yeah, if there is a code word in ZM of 2 that is not reached, or there is some element of ZM of 2 not reached by D, what that means is that we can send that message, and that message won't be an error, but we'll never be able to decode that into that message because D is not surjective. So, example 8.9. The even parity coding system developed to detect single errors in ASCII characters is an 8-7 block code. The encoding function is e of x7, x6 all the way to x1 is equal to x8 and x7 all the way to x1. So what we do is we add x8 is equal to x7 plus x6 all the way to x1 with addition in zmod 2. Now, let x equal x1 to xn and y equals y1 to yn be binary tuples. The Hamming distance, or distance dxy between x and y, is the number of bits in which x and y differ. The distance between two code words is the minimum number of transmission errors required to change one code word into the other. The minimum distance for a code, dmin, is the minimum of all distances at dx and y, where x and y are distinct code words. The weight, w of x, of a binary code word x is the number of ones in x. Clearly, w of x is equal to d of x0, where z is the set of all zeros. So, that's very abstract. Let's go through some examples. First, example 8.10. Let x be equal to 10101, y equal to 11010, and z equals 00011 be all of the code words in some code C. Then we have the following Hamming distances. D of x, y is equal to 4, because we need to flip this bit, then this bit, then this bit, then this bit. We need to flip 4 bits to get from x to y. D of x to z is equal to 3, because we need to flip this bit, and this bit. And d of yz is likewise similar. dyz equals 3. The minimum distance for this code is 3. We also have the following weights. First, w of x is equal to 3, w of y is equal to 2, and w of 0 is equal to, wy equals to 3, and w of z is equal to 2, since it's just counting the number of ones. The following proposition lists some basic properties about the weight of a code word and the distance between two code words. The proof is left as an exercise. Okay. This is basically saying that, I'm going to bring in some topology for a second. This is basically saying that, given binary tuples, we're able to define a metric topology with the code words. So we're able to topologize and talk about continuity of continuity of functions between Zn and Zm. With the stuff of code words. It doesn't mean much since we have a finite set, and as such we'll have a discrete topology anyway. But it's cool that we can define this in the first place, and possibly if we take things out to a limiting process, this will give us a valuable, a colimit topology. Something nice in terms of that. So, anyways, instead of me ranting. 1. W of x is equal to d of x0. 2. D of xy is greater than or equal to 0. D of xy is equal to 0 exactly when x is equal to y. 4. D of xy is equal to d of yx. 5. D of xy is greater than or equal to d of xz plus d of zy. The weights in a particular code are usually much easier to compute than the Hamming distances between all code words in the code. If a code is set up carefully, we can use this fact to our advantage. Suppose that x is equal to 1101 and y equals 1100 are code words in some code. If we transmit 1101 and an error occurs in the rightmost bit, then 1100 will be received. Since 1100 is a code word, the decoder will decode 1100 as a transmitted message. This code is clearly not very appropriate for error detection. The problem is that d of xy is equal to 1. If x equals 1100 and y equals 1010 are code words, then d of xy is equal to 2. If X is transmitted and a single error occurs, then Y can never be received, because we need to flip 2 bits to get from X to Y. So if we only flip 1 bit, we can never get from X to Y. Table 8.12 gives the distances between all 4-bit code words, in which the first 3 bits carry information and the 4th is an even parity check bit. We can see that the minimum distance here is 2. Hence, the code is suitable as a single error detection code. So we have 0 to a bunch of 2's, some 4's even for very large numbers, and otherwise we have 2's. Notice here we don't have any 1's in the table. That's what we care about for it to be a single error detection code. To determine exactly what the error detecting and error correcting capabilities for a code are, we need to analyze the minimum distance for each code. Let X and Y be code words. If d of x, y equals 1, and an error occurs where X and Y differ, then X is changed to Y. The received code word is Y, and no error message is given. Now, suppose d of x, y is equal to 2. Then a single error cannot change X to Y. Therefore, if d minimum is equal to 2, we have the ability to detect single-digit errors. However, suppose that dx and y equals 2 is y is sent, and a non-code word z is received, such that d of xz equals d of yz equals 1. Then the decoder cannot decide between x and y, because there is this element z that's 1 flip away from both a x and a y. Even though we are aware that an error has occurred, we do not know what the error is, because the error, which would be z in this case, well, I mean, it's just something where x and y are different from 1. We can't tell which one we want to initially go to. Suppose d minimum is greater than or equal to 3. Then the maximum likelihood decoding scheme corrects all single errors. Starting with a code word x, an error in the transmission of a single bit gives y with dxy equals 1, but dzy equal greater than or equal to 2 for any other code word z and not equal to x. If we do not require the correction of errors, we can then detect multiple errors when a code has a minimum distance then that is greater than or equal to 3. Theorem 8.13. Ooh, alright, this is going to be spicy. Alright, let C be a code with d min equal to 2n plus 1. Then C can correct any n or fewer errors. Furthermore, any 2n or fewer errors can be detected in C. Proof. Suppose that a code word x is sent and the word y is received with at most n errors. Then d of xy is less than or equal to n. If z is any other code word, or is any code word other than x, then 2n plus 1 is less than or equal to dxz is less than or equal to dxy plus dyz is less than or equal to n plus dyz. And hence, dyz is greater than or equal to n plus 1, and y will be correctly decoded as x. Now, suppose that x is transmitted and y is received, and that at least one error has occurred, but not more than 2n errors. Then 1 is less than or equal to dxy is less than or equal to 2n. Since the minimum distance between code words is 2n plus 1, y cannot be a code word. Consequently, the code can detect between 1 and 2n errors. Example 8.14. In table 8.15, the code word C1 equals 00000, C2 equals 001111, and C3 equals 111100, and C4 equals 11011 determine a single error correcting code. Table 8.5. Hamming distances for an error correcting code. So we see, just like using the normal binary differences, we have this has 3 differences, this has 3 differences, and we have either 0, 3, or 4 differences for all of them. So we can correct single-digit errors and detect 2-digit errors. Historical note. Modern coding theory began in 1948 with Claude Shannon's paper, A Mathematical Theory of Information. This paper offered an example of an algebraic code, and Shannon's theorem proclaimed exactly how good codes could expect to be. Richard Hamming began working with linear codes at Bell Labs in the late 1940s and early 1950s after becoming frustrated because the programs that he was running could not recover from simple errors generated by noise. Coding theory has grown tremendously in the past several decades. The Theory of Error Correcting Codes by Mac Williams and Sloan, published in 1977, already contains over 1,500 references. Linear codes, Reed Muller and 32-6 block codes, were used on NASA's Mariner space probes. More recent space probes such as Voyager have used what are called convolution codes. Currently, very active research is being done with GOPA codes, which are heavily dependent on algebraic geometry. Alright, before we continue, we still have a fair amount more. Yeah, we have a lot more. Oh, this is going to be very fun. I'm actually really hyped for that. Alright, but before we continue this though, I'm going to grab a cup, scroll back up, grab a cup of coffee real quick. Oh, this coffee's good. This coffee is good. Okay. How? I'm hearing my voice from Twitch because I'm on Stream Manager, but I can't see my screen at all. This is bizarre. Wait, let me just quick double check that it's working. Because if it's not working, we're going to have a problem. Alright. Alright, let's check this. Hang in there, we are loading your activity. Please do so. I have time. It's 2 a.m. Oh, I've only been streaming for 30 minutes, dang. Honestly, thinking about this reading might be the first reading that takes me up to an hour or more of pure just reading. Because this is a ton. Okay. It looks like we're doing fine. Okay, time to get back into it. 8.2 Linear Codes. To gain more knowledge of a particular code and develop more efficient techniques of encoding, decoding, and error correction, we need to add additional structure to our codes. One way to accomplish this is to require that the code also be a group. A group code is a code that is a subgroup of Zn sub 2. To check that a code is a group code, we need only verify one thing. If we add any two elements in the code, the result must be an n-tuple that is again in the code. It is not necessary to check that the inverse of the n-tuple is in the code, since every code word is its own inverse, nor is it necessary to check that 0 is a code word. For instance, 11000101 plus 11000101 equals 00000. Example 8.16. Suppose we have a code that consists of the following 7 tuples. It is a straightforward though tedious task to verify that this code is also a subgroup of C72. So, okay. I will update this on the board. So, we take this. We fix this as I probably should have just done a while ago. To bring, oh gosh. To bring that up here. Bring all this up here. So, group code. If E of Z 2 of M is a group. Alright. This code is a single digit error correcting and single error correcting code, but it is a long and tedious process to compute all the distances between pairs of code words to determine that d-min is equal to 3. It is much easier to see that the minimum weight of all the non-zero code words is 3. As we will see, this is no coincidence. However, the relationship between weights and distances in a particular code is heavily dependent on the fact that the code is a group. Alright. Stream, why do you do this? Please just work. Okay, I'm just going to assume the stream is working to save time. So lemma 8.17. Let x and y be binary n-tuples. Then w of x plus y equals d of x, y. Proof. Suppose that x and y are binary n-tuples. Then the distance between x and y is exactly the number of places in which x and y differ. But x and y differ in a particular coordinate exactly when the coordinate sum is 1. Since 1 plus 1 equals 0, 0 plus 0 is equal, but 1 plus 0 is equal to 1, and 0 plus 1 is equal to 1. Consequently, the weight of the sum must be the distance between the two code words. Theorem 8.18. Let d-min be the minimum distance for a group code C. then dmin is the minimum weight of all the non-zero code words in Z. That is, dmin is equal to the minimum of wx with x not equal to 0. Proof. Observe that dmin is equal to the minimum of dxy, where x not equal to y, is equal to the minimum of dxy with x plus y not equal to 0, is equal to the minimum of w of x plus y, where x plus y not equal to 0, and is the minimum, as such, of w of z with z not equal to 0. Since x plus y will always just be z, and any other valid such z will just be, well, it'll just be some x plus y, because we have a group. So, linear codes. From example 8.16, it is now easy to check that the minimum non-zero weight is 3. Hence, the code does indeed detect and correct all single errors. We have now reduced the problem of finding good codes to that of generating group codes. One easy way to generate group codes is to employ a bit of matrix theory. Define the inner product of two binary n-tuples to be x times y equals x1 y1 plus x2 y2 plus all the way on to plus xn yn, where x equals x1 x2 all the way to xn transpose, and y equals x y1 y2 all the way to yn transpose are column vectors. So also, since we will be working with matrices, we will write binary n-tuples as column vectors for the remainder of the chapter. For example, if x equals 0, 1, 1, 0, 0, 1 transpose, and y equals 1, 1, 0, 1, 0, 1 transpose, then x plus y, x times y is equal to 0. We can also look at inner products as the product of a row matrix with a column matrix. That is, x times y is equal to x to the t, y, is equal to x1, x2 all the way to xn, y1, y2 all the way to yn, is equal to x1, y1 plus x2, y2 all the way to xn, yn. Example 8.19. Suppose that the words to be encoded consist of all binary 3 tuples, and that our encoding scheme is even parity. To encode an arbitrary 3 tuple, we add a 4th bit to obtain an even number of 1s. Notice that an n-tuple x equals x1, x2 all the way to xn transpose has an even number of 1s exactly when x1 plus x2 plus all the way on plus xn equals 0. Hence, a 4-tuple x equals x1, x2, x3, x4 has an even number of 1s if x1 x plus x2 plus x3 plus x4 equals 0, or that x times 1 equals x to the t1 equals x1, x2, x3, x4 times 1, 1, 1, 1 equals 0. This example leads us to hope that there is a connection between matrices and coding theory. Also, I will just note as well that this is all mod 2, because we're looking for an even number of 1s. Let m of m times n of z2 denote the set of all m times n matrices with entries in z2. We do matrix operations as usual, except that our addition and multiplication operations occur in z mod 2. Define the null space of a matrix H and M of m times n z2 to be the set of all binary n tuples x, such that hx is equal to 0. We will denote the null space of a matrix H by null of H. Example 8.20. Suppose that H is equal to, I'm not even going to read this whole thing out loud. This is just, you can see the matrix. For a 5-tuple x equals x1, x2, x3, x4, x5 to be in the null space of H, hx equals 0. Equivalently, the following system of equations must be satisfied. x2 plus x4 equals 0, x1 plus x2 plus x3 plus x4 equals 0, x3 plus x4 plus x5 equals 0. The set of binary 5 tuples satisfying these equations are 0, 0, 0, 0, 1, 1, 1, 1, 0, 1, 0, 1, 0, 1, and 0, 1, 0, 1, 1. This code is easily determined to be a group code, since adding any two numbers in this null space gets us another member of the null space. Okay, theorem 8.21. Let H be an m times n, z mod 2. Then the null space of H is a group code. Note that we're being specific here. The null space of H is a group code. Proof. Since each element of z mod 2 each n tuple is its own inverse, the only thing that really needs to be checked here is closure. Let x and y be a null of H for some matrix H and m of m times n z mod 2. Then h of x equals 0 and h of y equals 0. So h of x plus y equals h of x plus h of y equals 0 plus 0 equals 0. Hence, x plus y is in the null space of H, and therefore must be a code word. A code is a linear code if it is determined by the null space of some matrix H in M times n, Z mod 2. So, example 8.22. Let C be the code given by the matrix, this disgusting thing. Suppose that the 6 tuple x equals 010011 t is received. It is a simple matter of matrix multiplication to determine whether or not x is a code word. Since h of x is equal to 011 is not equal to 0, the received word is not a code word. We must attempt to either correct the word or request that it be transmitted again. Parity check and generator matrices. Oh gosh. Stream's having a moment. Stream's working? Stream's working? Yeah, stream's working, okay. Parity check and generator matrices. We need to find a systematic way of generating linear codes as well as fast methods of decoding. By examining the properties of a matrix H and by carefully choosing H, it is possible to develop very efficient methods of encoding and decoding messages. To this end, we will introduce standard generator and canonical parity check matrices. First, suppose that H is an m times n matrix with entries in Z mod 2 and n greater than m. If the last m columns of the matrix form the m times m identity matrix I sub m, then the matrix is a canonical parity check matrix. More specifically, H equals A vert I sub m, where I is the m times n minus m matrix, a standard matrix representation. I don't know a proper way to read off that matrix. And IM is the m times m identity matrix as follows. With each canonical parity check matrix, we can associate an n times n minus m standard generator matrix. Alright, for this as well, note that H is this, visually, is this matrix followed by this matrix. And G is this matrix, the n minus m identity matrix on top and A on the bottom. Our goal will be to show that an x satisfying gx equals y exists if and only if hy is equal to 0. Given a message block x to be encoded, the matrix G will allow us to quickly encode it into a linear code word y. Example 8.23. Suppose that we have the following 8 words to be encoded: 001, 000, 001, 010, all the way up to 111. So all the binary 3 tuples. For A equal to 011, 110, 101, the associated standard generator and canonical parity check matrices are G is equal to, notice we have the identity matrix up here with these 3 rows, and then we have the matrices down here. And we have the matrices here with these being the standard 3x3 identity, respectively. Observe that the rows in H represent the parity checks on a certain bit positions in a 6 tuple. The ones in the identity matrix serve as parity checks for the ones in the same row. If x is equal to x1, x2, x3, x4, x5 up to x6, then 0 is equal to hx is equal to x2 plus x3 plus x4, x1 plus x2 plus x5, and x1 plus x3 plus x6, which yields a system of equations x2, x3, x4 equals 0, x1 plus x2 plus x5 equals 0, and x1 plus x3 plus x6 is equal to 0. Here, x4 serves as a check bit for x2 and x3, x5 is a check bit for x1 and x2, and x6 is a check bit for x1 and x3. The identity matrix keeps x4, x5, and x6 from having to check on each other. Hence, x1, x2, and x3 can be arbitrary, but x4, x5, and x6 must be chosen to ensure parity. The null space of H is easily computed to be 0000000, 001101, 0101110, 0110011, 1000011, 1001110, 110101, and 111000. An even easier way to compute the null space is with the generator matrix G, as we see this table here, where it gives us our message and it gives us our code word. And we're able to directly generate these messages from the code words. Or code words from the messages. Theorem 8.25. If H is an M times n, Z mod 2 is a canonical parity check matrix, the null of H consists of all x in Z mod 2 of n, whose first n minus m bits are arbitrary, but whose last m bits are determined by hx equals 0. Each of the last m bits serves as an even parity check bit for some of the first n minus m bits. Hence, H gives rise to an n minus m block code. We leave the proof of this theorem as an exercise. In light of the theorem, the first n minus m bits in X are called the information bits, and the last m bits are called the check bits. In example 8.2.3, or example 8.23, the first 3 bits are the information bits, and the last 3 are the check bits. Theorem 8.26. Suppose that G is an n times k standard generator matrix. Then C is equal to the set y is equal to gx equals y for x and z mod 2 of k is an nk block code. More specifically, C is a group code. Proof. Let g of x1 equals y1 and g of x2 equals y2 be 2 code words. Then y1 plus y2 is in C, since g of x1 plus x2 equals g of x1 plus g of x2 equals y1 plus y2. We must also show that two message blocks cannot be encoded into the same code word. That is, we must show that if g of x is equal to g of y, then x equals y. Suppose that g of x is equal to g of y. Then g of x minus g of y equals g of x minus y equals 0. However, the first k coordinates in g of x minus y are exactly x1 minus y1 all the way to up to xk minus yk, and since they are determined by the identity matrix ik part of G. Hence, g of x minus y equals 0 exactly when x equals y. That's actually extremely clever. So the way we put in the identity matrix makes it so that when we subtract this, we have that these are our first k terms in the tuple that we receive. And if that's equal to 0, well then they're equal to each other. Like, just by definition. That's clever. I like that. Before we can prove the relationship between canonical parity check matrices and standard generating matrices, we need to prove a lemma. Lemma 8.27. Let H equal A vert IM be an m times n canonical parity check matrix, and G equals I to the n minus m A be the corresponding n times n minus m standard generator matrix. Then HG is equal to 0. So in a sense, what this is also saying is that every output of G is in the kernel of H. Note that's something being said by this lemma as well. So proof. Let C equal HG. The ijth entry in C is, disgusting matrix stuff, Cij is equal to the sum from k equals 1 to n, hik gkj. We expand this out and just literally like break this sum up into sections. Equals the sum from k equals 1 to n minus m, h of ik, g of kj, plus sum from k equals n minus m plus 1 to n of h of ik, g of kj, is equal to, using the fact that we have the identity metrics there, k equals 1 to n minus m of aik, delta kj, plus the sum from k equals n minus 1 m to plus 1 to n of delta I minus m minus n, k, a of kj, which is equal to, just the Kronecker delta, aij plus aij, which because we're working mod 2, is equal to 0, where delta ij is the Kronecker delta. Theorem 8.28. Let H be the matrix with A on the left and the right be IM, be an m times n canonical parity check matrix, and let G equals I n minus m over A be the n times n minus m standard generator matrix associated with H. Let C be the code generated by G. Then Y is in C if and only if, so a converse, HY is equal to 0. In particular, C is a linear code with canonical parity check matrix H. Proof. First, suppose that Y is in C. Then Gx is equal to Y for some x in Z mod 2 to the m. By lemma 8.27, which is just the previous composition lemma, Hy equals Hg of x equals 0. So we've done all the work for this first case. Conversely, suppose that Y equals Y1 all the way to Yn is in the null space of H. We need to find an x in Z mod 2 of n minus m such that Gx transpose is equal to Y. Since hy equals 0, the following set of equations must be satisfied, which is of the form ai1y1 plus ai2 y2 plus all the way up to ai n minus m y of n minus m plus y to the n minus m plus 1 or plus I is equal to 0. Equivalently, yn minus m plus 1 all the way up to yn are determined by y1 all the way up to yn minus m. Consequently, we can let xi equals yi for I equals 1 all the way up to n minus m. Yeah, this is just standard like linear algebra system of equations manipulation stuff. So there's not going to be much gain from me reading that out loud. It's just going to probably make it sound more confusing. But essentially we have these set of equations that must be satisfied. And since we know that these are determined by those, we can just set these to be equal to their sums. And then we can just let xi equals yi. And by these certain bounds that we have on the parity check and the other stuff of the matrices, we know that it will be a valid number in z n minus m. Like we won't have to go over this limit of n minus m. It would be helpful if we could compute the minimum distance of a linear code directly from its matrix H in order to determine the error detecting and error correcting capabilities of a code. Suppose that E1 is equal to 1, 0, 0, 0, E2 is equal to 0, 1. So we have that E sub I has the ith coordinate being equal to 1, every other coordinate is 0. And these are the n tuples in Z mod 2 of n of weight 1. For an n times n binary matrix H, HEI is exactly the ith column of H. So, just as you can see like that, we pull out this column here. This is just basic matrix multiplication stuff. So we state the following result. We state this result in the following proposition and leave the proof as exercise. So, proposition 8.30. Let E sub I be the binary n tuple with a 1 in the ith coordinate and zeros elsewhere. And suppose that H is an m times n of Z mod 2. Then, HEI is the ith column of the matrix H. Wait, that's true for anything, if you have a basis. I don't know why they're asking us to prove it here, but I'll probably still prove it later, because it feels like a really good trip down memory lane. So theorem 8.31, let H be an m times n binary matrix. Then the null space of H is a single error detecting code if and only if no column of H consists entirely of zeros. Proof. Suppose that null of H is a single error detecting code, then the minimum distance of the code must be at least 2. Since the null space is a group code, it suffices to require that the code contain no code words of less than weight 2 other than the 0 code word. That is, EI must not be a code word for I equals 1 all the way to n. Since HEI is the ith column of H, the only way in which EI could be in the null space of H would be if the ith column were all zeros, which is impossible. Hence, the code must have the capability to detect at least single errors. Conversely, suppose that no column of H is a 0 column. By proposition 8.30, this proposition up here, oh god, internet, please speed up so I can scroll down. Conversely, suppose that no column of H is a 0 column. By proposition 8.30, HEI is not equal to 0. Example 8.32. If we consider the matrices H1 and H2, then the null space of H1 is a single error detecting code, and the null space of H2 is not, because in H2 we have this column right here. We can do better than theorem 8.31. This theorem gives us conditions on a matrix H that will tell us the minimum weight of the code formed by a null space H is 2. We can also determine when the minimum distance of a linear code is 3 by examining the corresponding matrix. Example 8.33. If we let H equals 111, if H equals 1110, 1001, and 1100, and want to determine whether or not H is the canonical parity check matrix for an error correcting code, it is necessary to make certain that null of H does not contain any 4 tuples of weight 2. That is, 1100, 1010, 1001, 0110, 0101, and 0011 must not be a null of H. The next theorem states that we can indeed determine that the code generated by H is an error correcting code by examining the columns of H. Notice in this example that not only does H not have any 0 columns, but that no 2 columns of H are the same. Theorem 8.34. Let H be a binary matrix. The null space of H is a single error correcting code if and only if H first does not contain any 0 columns, and no two columns of H are identical. Proof. The n tuple EI plus EJ has 1s in the ith and the jth entries and 0s elsewhere. And W of EI plus EJ equals 2 for I not equal to j. Since 0 is equal to H of EI plus EJ equals H of EI plus H of EJ can only occur if the ith and jth columns are identical, the null space of H is a single error correcting code. Suppose now that we have a canonical parity check matrix H with 3 codes. Then we might ask how many more columns can we add to the matrix and still have a null space that is single error detecting and single error correcting. Since each column has 3 entries, there are 2 to the 3 equals 8 possible distinct columns. We cannot add the columns 0, 0, 0, 1, 0, 0, 0, 1, 0, and 0, 0, 1. So we can add as many as 4 columns and still maintain a minimum distance of 3. In general, if H is an m times n canonical parity check matrix, then there are n minus m information positions in each code word. Each column has m bits, so there are 2 to the m possible distinct columns. It is necessary that the column 0, e1, all the way up to em be excluded, leaving 2 to the m minus 1 plus m remaining columns for information if we are still able to maintain the ability not only to detect, but also to correct single errors. Efficient decoding. Section 8.4. We are now at the stage where we are able to generate linear codes that detect and correct errors fairly easily, but it is still a time-consuming process to decode a received n tuple and determine which is the closest code word, because the received n tuple must be compared to each possible code word to determine the proper decoding. This can be a serious impediment if the code is very large. Example 8.35. Given the binary matrix H as follows, and the 5 tuples x equals 1, 1, 0, 1, 1 transpose and y equals 0, 1, 0, 1, 1 transpose, we can compute that hx equals 0, 0, 0 and hy equals 1, 0, 1. Hence, x is a code word and y is not, since x is in the null space and y is not. Notice that hy is identical to the first column of h. In fact, this is where the error occurred. If we flip the first bit in y from 0 to 1, then we obtain x. If H is an m by n matrix and x is in Z mod 2 of n, then we say that the syndrome of x is hx. The following proposition allows the quick detection and correction of errors. Proposition 8.36. Let the m by n binary matrix H determine a linear code and let x be the received n tuple. Write x as x equals c plus e, where c is the transmitted code word and e is a transmission error. Then the syndrome hx of the received code word x is also the syndrome of the error e. Proof. The proof follows from the fact that hx equals h of c plus e equals hc plus he equals 0 plus he equals he. The proposition tells us that the syndrome of a received word depends solely on the error and not on the transmitted code word, one of the benefits of working in the null space. The proof of the following theorem follows immediately from proposition 8.36 and from the fact that he is the ith column of the matrix H. Theorem 8.37. Let H be an m of m times n Z mod 2, and suppose that the linear code corresponding to H is single error correcting. Let R be a received n tuple that was transmitted with at most 1 error. If the syndrome of R equals 0, then no error has occurred. Otherwise, if the syndrome of R is equal to some column of H, say the ith column, then the error has occurred in the ith bit. Example 8.38. Consider the matrix H equals, that's a large matrix, I'm not going to read that whole thing off. And suppose that the 6 tuples x equals 1, 1, 1, 1, 1, 1, 0, y equals 1, 1, 1, 1, 1, 1, and z equals 0, 1, 0, 1, 1, 1 have been received. Then hx equals 1, 1, 1, h of y equals 1, 1, 0, and h of z equals 1, 0, 0. Hence, x has an error in the 3rd bit, and z has an error in the 4th bit. The transmitted code words for x and z must have been 110110 and 010011 respectively. The syndrome of y does not occur in any of the columns of H, so multiple errors must have occurred to produce y. Coset decoding. We can use group theory to obtain another way of decoding messages. A linear code Z is a subgroup of Z mod 2n. Coset or standard decoding uses the cosets of Z and Z mod 2n to implement maximum likelihood decoding. Suppose that C is an n by m linear code. A coset of C in Z mod 2 of n is written in the form x plus c, where x is in Z mod 2 of n. By Lagrange's theorem, there are 2 to the n minus m distinct cosets of C in Z mod 2 of n. Example 8.39. Let's see the 5x3 linear code given by the parity check matrix as follows. The code consists of the code words 0000, 01101, 10011, and 11110. There are 2 to the 5 minus 2 equals 2 to the 3 cosets of C in Z mod 2 of 5, each with order 2 to the square, 2 squared equals 4. These cosets are listed in table 8.4a. As we can see above, I'm not going to belabor the exact coset and its computation here. Our task is to find out how knowing the cosets might help us decode a message. Suppose that X was the original code word sent and that R is the end tuple received. If E is the transmission error, then R equals E plus X, or equivalently, X equals E plus R. Excuse me. Yes, because subtracting by either X or R is the equivalent of either adding by X or R because we're working in mod 2 tuples. However, this is exactly the statement that R is an element of the coset E plus C. In maximum likelihood decoding, we expect the error E to be as small as possible. That is, E will have the least weight. An n tuple of least weight in a coset is called a coset leader. Once we have determined a coset leader for each coset, the decoding process becomes a task of calculating R plus E to obtain X. Example 8.41. In table 8.40, notice that we have chosen a representative of the least possible weight for each coset. These representatives are coset leaders. Now, suppose that R equals 01111 is the received code word. To decode R, we find that it is in the coset 00010 plus C. Hence, the originally transmitted code word must have been 01101 equals 01111 plus 00010. A potential problem with this method of decoding is that we might have to examine every coset for the received code word. The following proposition gives a method of implementing coset decoding. It states that we can associate a syndrome with each coset. Hence, we can make a table that designates a coset leader corresponding to each syndrome. Such a list is called a decoding table. Alright, so proposition 8.43. Let C be an n-k linear code given by the matrix H, and suppose that X and Y are in Z mod 2n. Then X and Y are in the same coset of C if and only if H of X is equal to H of Y. That is, two n tuples are in the same coset if and only if their syndromes are the same. Proof. Two n tuples X and Y are in the same coset of C exactly when X minus Y is in C. However, this is equivalent to H of X minus Y equals 0, or H of X equals H of Y. Example 8.44. Table 8.42 is a decoding table for the code C given in example 8.39. If X equals 01111 is received, then its syndrome can be computed to be HX equals 010, and examining the decoding table, we can determine the coset leader is 00010. It is now easy to decode the received code word. Given an n-k block code, the question arises of whether or not coset decoding is a manageable scheme. A decoding table requires a list of cosets and syndromes, one for each of the 2 to the n minus k cosets of C. Suppose that we only have a 3224 block code. We have a huge number of code words, 2 to the 24, yet there are only 2 to the 32 minus 24 equals 2 to the 8 equals 256 cosets. So, reading questions. Okay, let me clear the whiteboard in preparation for this. So, alright, suppose a binary code has a minimum distance d equals 6. How many errors can be detected and how many errors can be received? So if I remember correctly, a binary code of minimum length 2k, or actually, so if we can detect double-digit errors, that means it's definitely at least 3 errors that can be detected. If I remember correctly. Oh wait, is it 3 or is it 2? 2 errors can be computed. Okay. Suppose it has a minimum just how many errors can be detected, how many errors can be corrected. So we can detect errors up to 5. We can only correct errors up to either 3 or 2. let me double check what that is. By the way, let me just quick mark this page. So this is page 121. Scrolling up through all this. Going up through this. Let's CPA code with d minimum is equal to 2 and plus 1. See, you can correct enter fewer errors anymore. Alright, so in this case, it'd likely be 2 errors. Since if we have 3 errors, we can have a 3 error that is like exactly a distance of 3 between one and the other. So we'd be able to correct 2 errors, and we'd be able to notice 5 errors. Okay. Explain why it is impossible for the 8-bit string with decimal value 56 base 10 to be an ASCII code for a character. Assume the leftmost bit of the string is being used as a parity check bit. What I'm going to assume is that the 8-bit string, so if we convert this to base 2, we're going to get a number that is, oh gosh, 56 to binary. Google, help me. So yeah, it'd be 0, 1, 1, 1, 0, 0, 0. So it'd be a number that has a odd parity. And as such, it would be impossible for it to be a ASCII code. Suppose we receive the 8-bit string with decimal value 56 when we are expecting an ASCII character with a parity check bit in the first bit. We know an error occurred in transmission. Give one of the probable guesses for which character was actually sent other than 8. Under the assumption that any individual bit is rarely sent as an error. Explain the logic in your answer. You mean to consult a table of ASCII values online. Then I'm too lazy for that. Okay. Suppose a linear code C is generated with the null space of the parity check matrix 0, 1, 0, 1, 0, 1, 1, 1, 1, 1, 0, and 0, 0, 1, 1, 1. Then x equals 1, 1, 1, 0, 0 is not a code word. Describe a computation and give the results of a computation which verifies that x is not a code word of C. So if x were a code word of C, then x would be in the null space of H. So we simply just need to do like a matrix multiplication. Or actually, so H, okay. Describe computation with results of a computation that verifies the parity check matrix. Let me think of how they want to do this. Oh wait, no, yeah, actually, wait, what am I thinking? Yeah, we would literally just do a computation. So it'd be 0, 1, 0, 1, 0, 1, 0. 1, 1, 1, 1, 0. 1, 1, 1, 1, 0. And 0, 0, 1, 1, 1. 0, 0, 1, 1, 1. And we want to confirm that, what was it? 1, 1, 1, 0, 0. So 1, 1, 1, 0, 0. Because all our code words are going to lie in the null space of this. So if this is like not in the null space, this cannot be a code word. So we compute it and we get 1 in our numerator. Already we're done. So like basically 1, 1, 1, 0, 0. We're just going to have 1 in here. So it doesn't even matter what these two are. We already have something is not in the null space of H. Okay. So For h and x in the previous question, suppose that x is received as a message. Give a maximum likelihood decoding of the received message. So most likely it would be that the fifth digit would be converted to a 1, correct? Actually, no, it would be the second digit, because... Wait, I'm actually trying to think about this more critically. So first of all, if x equals 110 is not a code word, right? Then either the first or the second digit needs to be flipped. Right? Either the first or the second digit needs to be flipped in order to fix that numerator issue. Or the second and the fourth digit. If the second digit is flipped, oh wow, that's actually kind of nasty. You would need to flip both the second and the fourth digit. Or the second and fifth, fourth and fifth. Yeah, okay. Yeah, okay. That was definitely rough. This section is a lot to handle. This has probably been the most I've done out of a reading. And I've probably still missed details because just look at this. Just look at this. It is a ton. I think this is one of the only chapters that is like 20 pages plus long. Alright, so we're going to be doing the exercises. God knows we're going to be doing the exercises. Let me scare myself by looking at how many there are. Not that many, but still terrifying. So before we do that, I'm going to just spare myself, and I'm going to have an intermission to drink some coffee, run to the restroom, do what I need to do before we begin on these exercises. Alright, and I'm back. And I'm in part excited, in part scared for the exercises coming up. Alright, before I do worry about that though. Oh gosh, oh no. Chrome, why are you like this? Oh, why is my computer so laggy? Oh god. Okay, you're gonna have to give me a minute to fix this. Let me go back to the standard textbook. Oh my gosh, this lag is bad. Oh my. Alright, I might have to like reload the page. Yeah, I'm gonna have to reload the page. So it's 122 is where the exercises are. Alright, we're gonna wait for this to load. We're gonna hope that this loads sometime over the course of my lifetime. Okay, so hopefully putting in a page number doesn't make this web page spontaneously explode. Alright, do I have the ability to still scroll up and down? Yes, okay, good. Alright, so now that that's out of the way, let me double check the stream is actually going. Because I do not want to deal with a bunch of exercises that are probably going to be partially exhausting. Exhausting in a good way, but exhausting nonetheless, without knowing that they're going to be recorded. So let me grab a drink. Open a drink while we're worrying about that. Alright. Looks like we're loaded in. We're loaded and delayed, but we're loaded in, boys. Okay. So first, why is the following encoding scheme not acceptable? It's because we have both 1 and 8 sent to the same code word. If we're given the code word 001, we cannot uniquely decrypt it. Without doing any addition, explain why the following set of 4 tuples in zmod 2.4 cannot be group code. There's no 0 in here, because if we add any of these to themselves, it's 0, and we don't have the 0. Compute the Hamming distances between the following pairs of n tuples. So the way, if you want to visually get an algorithm for it, is we'll line them up like this. So it'll be 0, 1, 1, 0, 1, 1, 0, 1, 0, 0, 1, 0. And then we're going to have 0, 1, 1, 1, 0, 0, 0, 1, 1, 1, 0, 0. And then we're going to binary add them. So I'll put add mod 2 here, which will give us 0. This will go to 0 because 1 plus 1 mod 2 is 0. 0, 1, 1, 0. And from this, we can just take, I'll put the opposite value, which means that it's going to be 1 plus 1 equals 2. So d of 0, 1, 1, 0, 1, 0 and 0, 1, 1, 1, 0, 0 equals 2. Okay, so, and then we just do that algorithm similarly for anything else. Compute the weights of the following n tuples. So we have, the weights are literally just going to be the number of ones. So 1, 1, 0, 1, 0. So this is going to have a weight of 3. This is going to have a weight of 4, 5, 6. This is going to have a weight of 4. This is going to have a weight of 3. So suppose that a linear code C has a minimum weight of 7. What are the error detection and error correction capabilities of C? So we know that 7 is equal to 2 times 3 plus 1. So we can detect 2 times 3 equals 6-bit errors, and we can correct 3-bit errors. In each of the following codes, what is the minimum distance for the code? What is the best situation we might hope for in connections with error detection and error correction? Okay, I'm just gonna, especially because this one looks like a nightmare, I'm just going to be doing A. So we have, oh gosh, this is really gonna be painful. 0, 1, 1, 0, 1, 0. So this will have a distance, these two will have a distance of 3. Actually, let me just look, are there any obvious counterexamples? 0, 1, 1. These will have a distance of 2. This will have a distance of at least 2. This will have a distance of at least 2. This will have a distance of at least 2. This will have a distance of at least 2. This will have a distance of 2, yeah. So it looks like universally, this code has a distance of 2 between everything, which means that it will be a single-digit error detecting code. But because d minimum is greater than or equal to 2, actually it's equal to 2 because of that, it means that we will not be able to correct single-bit errors. So compute the null space of each of the following matrices. Which type of n, k block codes are the null spaces? Or what type of them? Can you find a matrix, not necessarily a standard generator matrix, that generates each code? Are your generator matrices unique? So for an example, just to make things fairly simple, let's have C. So we have 1, 0, 0, 1, 1. And 0, 1, 0, 1, 0, 1, 1. So we want the condition that x1 plus x4 plus x5 equals 0, or that x1 equals x4 plus x5, and we want the condition that x2 equals x4 plus x5. Which means as well that x1 is going to have to equal x2. And x3 actually doesn't matter for this. So we're going to have the matrices, the vectors of form x1, x1, x3, actually, because it doesn't really matter, we'll call this y, x4, x5. So for example, we're going to have, in this, we're going to have 0, 0, 0, 0, 0. We're going to have 1, 1, 0, 1, 0. 1, 1, 0, 0, 1. 1, 1, 0, or no, not 1, 1. Next we'll have the 0, 0, 1, 0, 0, and the 0, 0, 1, 1, 1. And we have this, and we also have the case for y equals 2. Which will give us a 10 code word code that generates each code. Now, can we find a matrix that generates the code? So let's think about this. So we're gonna have 3 inputs, and we're gonna have to transfer them to 5 things. So I'll make it standard that our third bit determines our middle number. 1, 1, 1, 1, 1, 1, 1, 1. So we know that the last bit, so we're going to have x, y, z. Then we know also we're going to have, we'll determine x1 by that, which means we're going to have x 0, 0. I don't need to worry about the parity on the parity on that. x3 can just be anything. Or actually no, because of that, we should have something like this. So yeah, z will control that. And now we'll have x is equal to 1. The thing is we have a choice with x4 and x5. So I don't know if because of that choice we won't be able to have a standard generating matrix. Check. Yeah, it looks like we won't be able to find a matrix that generates this code. Well, let me triple check. We'll have this, right? So now, the question is, we'll be able to find a y will probably determine which preset we have. Wait, what if, okay. I'm thinking not. So this sets the first bit. This sets x1. x2 is equal to x1. We're going to have this be set is equal to y. And we need the condition that y determines whether or not actually, wait. Would this work? And then if you just replaced it by like 1, 1 here. No, okay. There's too many parameters here. You can't have 3 numbers describe everything. Because you have 2 options for x4 and x5 in relation to x1. So those need to be controlled separately, but you also have to control the option that your third completely independent thing is like properly independent. So you need 4 degrees of freedom at least. Alright. So construct a 5-2 block code. Just tell us about the error. Now, we'll worry about the construction another day. Okay. Suppose that a 1, 0, 0, binary. Oh, this is like basic probability, okay. Which parents are parity are canonical parity check matrices. Alright, list all possible syndromes. Well, now. Okay, I want to get to the proof stuff. For each of the following matrices, find the corresponding code C. Let W, X, Y, and Z be binary-identicals. Proof each of the following statements first. So W of X is equal to D of X0. So W of X equals the number of ones in X. Which is equal to the number of digits in X. Digits in X. Differing from 0, which is equal to D of X 0. That's for the weight. Alright, D of X Y is equal to D of X plus Z, Y plus Z. I'm just going to do these informally with words, because there's not much you can get from them. But basically, if X and Y differ in, however many zeros, then since you're adding Z, if X and Y already differ in a place, then X plus Z, Y plus Z will still differ in that place. And if X and Y are the same in a place, then X plus Z, Y plus Z is going to be the same in that place. So it's not going to give you any new information, like shifting by Z. And then D of XY is equal to WX minus Y. And that is because you can subtract Y by both X and Y. So we basically have D of XY. That's actually a kind of satisfying line of our reasoning. D of X minus Y, Y minus Y equals D of X minus Y, 0 equals W of X minus Y. Alright, a metric on a set X is a map satisfying the other words. To prove that Hamming distance is a metric on Z2 of N, decoding a message structure reduces to deciding which is the closest code word in terms of distance. D of xy is greater than 0 because you can't have a negative number of zeros differing, because you're talking about the number of that differ. So this is like by definition. D of xy is equal to 0. Exactly when x equals y, because otherwise there's a digit differing, which means d of xy is greater than or equal to 1. D of xy equals d of yx, because they're both counting the difference in digits between x and y, just shifting that around when you say that. And then d of xy is less than or equal to d of xz plus d of zy. And this comes down to the fact that if there's a difference in, if there's a one, alright, so if there's a difference in digit I in x and y, then that means that given any other number z, there's either a difference in the ith digit between x and z, or a difference in the ith digit between z and y. So by definition, every digit in here that differs corresponds to a digit in one of these two, and summing them together you get inequality. Okay, let's see if linear code shows that either the ith coordinate of codes. Let's see if linear code shows that after code word has weight or exactly half weight. Show that code words in ways. Yeah. I mean, it makes sense. I forget if a linear code is a group code or not. Dual orthogonal code of C is find the dual code. Alright, oh, these are proper Hamming codes. The null space of a code MBO with ith column number I written in binary with m bits. The null space of such a matrix is called a Hamming code. Show that the matrix equals 9 generates a Hamming code. Codes having the maximum number of information with two checks are called perfect. Every possible syndromes. In this case, give an example showing the syndrome could represent multiple errors. So, yeah, a lot of these are. This is much more on the application-based side, which is not really what I like, where I want to go with the reading. There's a lot of cool things here, but there's not really that much of an incentive, because I'm self-studying all this. There's not much of an incentive for me to particularly care for a lot of this. This stuff, this is like where I'm interested in. This is where a lot of things meet together for me, abstractly. But the algebraic coding theory, not really my jam. So these books definitely, I've seen some people reference these books. I know they're good, but before that, I just want to double check one small detail. I want to make sure that linear codes, when they were introduced, are linear codes group codes by definition. Linear codes. So binary n tuples, linear codes. The inner product. So where do we actually define linear codes? Wait, I don't know if I can control F in here. Yeah, it doesn't look like it. There's a group code, we know I check that thing. No, wait, like so. Good codes. The inner product of two binary n tuples. Define the null space, be the binary. A code is a linear code if it is determined by the null space of some matrix. Okay. So yeah, by also that definition, the null space of a matrix is a group, since by linearity 0 is such 0, and then h of x plus y equals h of x plus h of y. If h of x and h of y are 0, then h of x plus h of y is equals to 0. So h of x plus y is equal to 0. Yeah. Man, a lot of this is like, there's so much stuff here, but it is not specifically. I'm not very specifically interested in it. And that's unfortunate, because there's otherwise a lot of really cool stuff. Yeah, I guess I'll leave it here. Also, I have marching band practice in like 7 hours, so I should probably like get to sleep or something. So I guess my standard thanks for tuning in. Have a wonderful day.